Hello guys, welcome to another exciting episode of PicoCTF challenges. We are Cybersensei. We are here to bring you a good one now from the cryptography angle, the cryptography domain of cybersecurity challenges. Still under PicoCTF 2026, you can get under original event PicoCTF 2026. Under cryptography, we are going to cover Black Cobra Pepper. So this was an exciting one. I did it myself. So Black Cobra Pepper, medium challenge, cryptography, and a PicoCTF 2026. So the description is, I'm just going to say peppers or peppers. It depends with your pronunciation. So into brackets, change. So there's the challenge and the output. I've already downloaded them. You can see they're already here. The child.py, this child.py, and the output. So we're going to look at the hints first of all. So does this remind you of any other popular encryption? So we are automatically know we are dealing with an encryption. So hint number 2, what purpose does the S box serve? So S box is another exciting feature you should understand. This commonly comes from IES, which is literally Advanced Encryption Standard. We'll get to understand it more today, and let's actually open this in a code editor. Nice, amazing. So we can see the code, exiting features from it. You can see define glue. This is a definition of glue, root word, subword, recon, exactly. So what I need you to understand from what this was testing, you have seen there's a hint that asks what purpose does the S box serve. So what is literally as an S box? An S box is literally a substitution box. It comprises of subbytes and subwords. Let's check if we can get subbytes and subwords. I believe they're there. I saw them somewhere. Subbytes, you can see subbytes. Let's see if you can get subwords. Not there. Subword, exactly this one. So you can see. So it literally comprises of subbytes and subword. The ones that I've literally highlighted. They take a number and swaps it with a different looking string. So when you have like a number like 475, it now swaps it with a different looking string such that somebody won't understand that it was originally the 475. It's more of an encryption method. It's literally an encryption method. That's why it someone must not understand what originally it was. So it changes it, and only the algorithm understands, only the function knows what that is. You're getting me? In the code, you understand, in the code we have talked of subbytes and subword. They should be shifting or changing and swapping that an input, the number it is taking, and giving another random string of numbers. But notice something. So subword, it's taking word as the input and returning what word. It doesn't change anything. It doesn't add anything to our variable word. So notice that's a flow, because it's supposed to add some random. It's supposed to swap it with some random string. Notice that. Then there's this other one that was subword with subbyte. Somewhere here, subbyte, exactly. Subbyte still does the same thing. It takes state as the variable, but still gives the exact state. Doesn't do anything on the state variable. That's a vulnerability. It doesn't meet the purpose of why it's a S box. It's a substitution box. It doesn't meet the purpose. Now, when you're dealing with S box in IAS, S box goes hand in hand with something called recon. This is a function, recon. I believe you can see it here. It's also here, and does the same thing. It's supposed to swap it. It's in full. It's a round constant. It's supposed to add some random noise. So it's not now swapping. You remember the S box, it was swapping with something else, but this one, it just adds some random noise. You can if you have solved some various CTFs, you can notice some at the end you come up with a flag that has some noise. You're supposed to clean it manually, but now in this algorithm and in this code and this specific function, it just adds that random noise. Instead of a literal word, it adds this word. I hope you're getting me. It's adding some random noise so that someone won't get the clean content or the clean data. So those are the key vulnerabilities of this. And notice, if SBox is not working, then this gives this result to something else. One thing you should know in matters of encryption, we always understand you're not supposed to get something linear. I'll give you an example where I'm calling it linear. You see, when we are adding a random noise, and we are swapping it with the random numbers or with random strings, it now gives that randomness. Let's just call it the word randomness, in that you can't actually calculate or figure out what key was used, what algorithm was used to come up with the output. Now, when all these are not put into consideration and when working with encryption, we come to get something called linear. In simple terms, what we call the linear progression, all those words, they just mean when you have a master key or when you have a key, you get to understand what was the rate of change. Let's give it that word. What was the rate of change? If this word, let's just use this word. If this word was being multiplied by 2, then you understand in another scenario the same word will be multiplied by 2. So if it was being added some 1, 2, 3 at the end, notice the same code will be doing that again and again. But the essence of using SBox and Recon, it was giving it random values, random noise, such that someone can't understand it. Once you get this, you can't get also the other one. Now I'll get to where we need to understand all this. Why we need to understand all this. You see, in this code where you have this challenge, which when run you get an output. We are given something called an output, right? So we can check the output. Notice in this, the code, how it was running, how the code ran, print the encryption of PT1, which PT1 is this. You notice that PT1 is this, and the key. So it prints this. So the value of this, the result of that, I'll do this. The result of that was this first output. That was the first output. The next thing, what the code was running, this last line. Notice, last line, the output. We have the output, which is this which is the second line. Notice we have things that are common here. The key, right? The key. We have the PT1. We don't have the key, but the key is common in both equations, and we have the outputs. So you just do this in like a normal math situation which you are doing in schools and everything. You can see the PT1. Let's give how these were obtained. The PT1 plus a key will result to this. Notice that. Then the flag which we are supposed to obtain, when you add the key, it's supposed to give you this output. Notice we have the outputs of both. We don't have the flag, but we have PT1, because PT1 we already have it. It was given as a variable here. This one, we can replace that notice it now makes everything perfect. You understand? We now need to get the flag, but in these two equations the key here is constant with this same key. They have the linear, because remember they are not changing. The main essence of SBox and Recon, they were supposed to make this key not be the same. You're not supposed to have the same key, but with the problem of having them in linear form, because SBox and Recon are not working, we can now get the master key. A master key is now the rate at which I was saying, like the rate at which it changes. If it was being added, let's say if it was a value like 146, if it was being added 10, it now becomes 156. Remember? And if now in another scenario it's 200, it still add the same 10 to get 210. I don't know if you're getting me. So with all that, we just now need to have a constant key. So I've written a script to do all these calculations for us, because we are dealing also with XOR and everything. And this encryption, I was literally using zeros as the key to factor here. I used zeros and to factor here, and you can get the script actually in our GitHub repository. I'm going to paste the link down in the description. The repository, the script will actually do everything for you. Not actually, it will actually do everything for you, but you need to understand whenever that encryption part doesn't work, that SBox part doesn't work, the key will remain constant, the master key will remain constant. But security features having that SBox and Recon, it makes sure someone doesn't get a master key, because remember there are instances or there are systems you're going to be using. You can if an attacker wants to test your system, they just give their input and check the output, then give another input and check the output. They just check the rate of change and they can get the key, right? So I'm going to download this, or let me just copy it and open terminal here. I believe that's the easiest way. I'm going to maximize that. Sudo nano sol.py. Paste. I'm going to paste it. Now I believe you can see it is utilizing everything we have, because it has PT1. The CT1 is the result and the CT flag. Remember whatever we are doing here. The PT1 is this one. It's going to utilize that. The CT1 is now the output of the results of when you use PT1. You can see it's using the D7 value, and we have the output of the flag after the flag is being used with the key. So you can see it's also using that. And then now the null key, as I have said, I'm going to use zeros. It's going to calculate everything. Don't worry. The script is going to do everything for you. Just going to save it, then do Python 3 solver.py, and it actually gets you the flag. Main thing to understand the encryption part, you have to make sure you don't have a master key. Master key can't be obtained by a hacker, because now you see here we obtained the master key. We just use them. A key, and it got us everything. Others, let's submit this flag. Let's see if it works. Hooray, you have solved this challenge correctly again. Others, thank you so much for watching. See you in the next one. Bye bye.